When an automated development environment runs at this blistering speed, more than a dozen discrete operations happen in mere seconds. A developer types a single, simple instruction into a command line interface, asking to refactor a file and run the test suite. From the outside, it appears as though the AI model is directly parsing the file system and performing these tasks autonomously. Relying purely on prompt engineering to govern these complex actions causes enterprise AI systems to hallucinate, drift, and fail in production. The equation for production AI development is this: an AI agent equals the model plus the application harness. The large language model only streams text and tool proposals. The reasoning comes from the model, but the operational reliability comes entirely from the harness. We can prove this by tracing the exact lifecycle of one user command through the 5 stages of the Claude Code architecture, built on TypeScript and Bun. Production-grade behavior, the loops, the memory structures, and the permissions, lives almost entirely outside the raw API call. The process begins when the user's terminal command hits the session-facing query engine via submit message. This is the core engine, an unbounded state machine called the queryLoop. A user turn spans dozens of rounds inside this loop. The continuation switch, needs follow-up, triggers on every tool use block, initiating another round. The loop exits once the model streams no further tool requests. Treating a turn as a single model call is a misconception that prevents developers from building reliable routines. The turn is the loop. Inside that loop, the model attempts to interact with the file system or an external network. Before the model even sees the tool registry, the harness pre-filters the available operations using strict deny rules. Operations are forbidden before the model can even propose them. This timeline shows streaming first execution via the streaming tool executor. Tool blocks are processed midstream. Execution concurrency relies on application metadata flags. Safe tools route to parallel tracks, while unsafe tools form a serialized queue, completely bypassing model discretion. An LLM has no native concurrency awareness. Masking network latency and managing execution state must be handled structurally by the application harness. Simultaneously granting a model access to private repositories, untrusted web content, and outbound networks creates a vulnerability for unauthorized data exfiltration. Every call passes a 3-stage gate via hasPermissionsToUseTool, preset rules, a transcript classifier, and a human approval queue. The classifier fails closed if unreachable. Denials are piped back as a tool result error, allowing the model to read restrictions and try alternate strategies. Professional agents enforce structured authorization logic rather than relying on a system prompt to prevent destructive actions. In AI system design, memory is an overloaded term. Conflating ephemeral context windows with long-term semantic retention leads to systems that lose project awareness once a session ends. The architecture separates 3 memory timescales. Tier 1 is the ephemeral working transcript. Tier 2 is durable semantic memory, protected by byte caps. Tier 3 is the auto-dream process, an independent sub-agent. Consolidation is double-gated, requiring 24 hours and 5 new sessions before distillation. Separating memory into discrete, time-bounded subsystems maintains project awareness across days of distinct sessions without exhausting the context window. Eventually, any long-running looping agent will reach the model's absolute token context window limit. This chart tracks context hygiene through the auto-compact threshold. When token usage crosses the line, lower chunks aggressively compress into a single summary block. The model now only sees this summary combined with the recent transcript tail. If an unforeseen response throws a prompt too long error mid-turn, the loop triggers a reactive recovery sequence. It attempts a context collapse drain of low-value blocks first. If that fails, it falls back to a full reactive compaction to save the session. Without these algorithmic compression mechanisms, long, tool-heavy turns would crash unconditionally. The turn is complete only when the model finally responds with plain text and 0 operational requests. The needs follow-up loop continuation flag toggles to false, terminating the unbounded state machine. The seamless user experience in the command line is the output of a massive orchestration engine executing underneath. Deploying enterprise AI solutions requires moving beyond the limitations of prompt engineering. Probabilistic reasoning from the model must be governed by these rigid, deterministic architectural controls. The LLM is merely the reasoning engine. The surrounding architecture is the reliability engine. Building a production-grade autonomous system fundamentally requires mastering harness engineering.